as well as the phasor transform, right? So the phasor transform, what is phasor, what a phasor is made up of, the time domain, and the phasor domain, or what we call the frequency domain. Okay, so for today, we will be having the phase difference. Okay, so for the phase difference, when we say phase difference, it is the angular displacement between waveforms of same frequency. Okay, it is, or if a certain angular displacement is zero, then the waveforms are in phase. Now if the angular displacement is not zero, or there is a certain value, okay, of this angular displacement, it means that they are out of phase by an amount of displacement. Okay, let's say for example we have this one. So we have our voltage 1 and voltage 2, which are given in what domain, in what form? They are given in what form? Hello? Are you there, my EE22S1? Do I have some students? Okay, so my question is, V1 and V2 are given in what domain? In time domain format. Okay, I hope you do replay the recording last time, because you must know how to determine these kinds of domain, or these kinds of setup, these kinds of format, because it is very necessary up until the end. Okay? Or else you might not get the idea. Okay? So V1 and V2 herein are in time domain format. Correct? So as you can see, V1, okay, what is the phase offset of V1? What is the phase offset of V1, or the phase angle of V1? We have V1 is equal to 5 sine 100t. What is now the phase angle of V1? Can't you see the PowerPoint? Ah, you can see it. That's why you're not. Why don't. Let me just share it again. Why it is not sharing? Okay, can you see now the screen? Okay, so as I said a while ago, phase difference is the angular displacement between waveforms of the same frequency. It means that you are comparing and contrasting different waveforms, or two different waveforms. Now, if the angular displacement is zero, then the waveforms are in phase. But if the angular displacement has its value, or it is not zero, it means that they are out of phase by a certain amount of displacement. Now we have an example here. So we have V1 is equal to 5 sine 100t, and V2 which is equal to 3 sine 100t minus 30 degrees. Now, my question is, what is the phase offset or the phase angle of V1? What is the phase offset or the phase angle of V1? 0 degrees. Very good. What about V2? Negative 30. Now, observing that V1 is a 0 degree or has a phase offset of 0 degree and V2 has a phase angle of negative 30 degrees, can I say that V1 leads V2 by 30 degrees? Yes. Okay. What about if I say V2 lags V1 by 30 degrees? Is that also correct? Okay. So that is what I am talking about. Okay. It means that there is a certain distance, okay, a certain displacement that differs these two waveforms. Okay. So on V1, since we have a phase offset of 0 degree, and in V2, since we have a phase offset of negative 30 degrees, it means that they are apart by 30 degrees. Now it's on a certain scenario, or they differ on a certain scenario wherein we can say that V1 leads V2 by 30 degrees, and we can also say that V2 lags V1 by 30 degrees. Okay? It means one is ahead and the second one is behind. Okay? And we can also say that the other is ahead and the other is behind. Did you get the idea? Did you get the idea? Okay. So going in here, we have a phase difference with phasor. So the waveform generated by the leading phasor leads the waveform generated by the lagging phasor. So let's say, for example, herein. So we have the IM, or the maximum current, which leads the maximum voltage. So we have the IM, which is in the blue arrow, and we have the VM, which is in the pink arrow. Okay, if we try to project this one into a certain waveform, we can actually say that there is this angle difference here, or phase angle difference here. Okay, the phase angle difference here therefore leads, or therefore our current in a time domain format, okay, leads our voltage in time domain format. It means this waveform, the blue waveform, is leading onto our pink waveform. Okay, now let's have an example. Okay, so we have an example here. This is the circuit. This is the original circuit. This one. Okay, so and we have a given. We have three givens. We have I1, which is 20 sine omega t milliamps. We have I2, which is 10 sine omega t plus 90 milliamps. And we have I3, which is 30 omega t minus 90 degrees milliamps. Determine the equation for I total. What is this kind of circuit? What is the connection of this circuit? What is the connection of this circuit? Parallel, okay. Since it is parallel, okay, according to the condition on your circuits 1, okay, since it is parallel, how can we get for the I total? If we have a complete parallel circuit, how can we get for the I total? What is the equation? Or what is the condition? What is the condition? Okay, in parallel, voltages are the same, but we are dealing with current. How can we get for the total current if we have or if we are on a parallel setup? Okay, we need to add all the individual currents in parallel, correct? To get the total current. Therefore, in order for us to get for the I total, we need to add I1, I2, and I3. Okay. So if we need to add I1, I2, and I3, can we already add I1, I2, and I3 being on a time domain setup? Hmm? Can we already add I1, I2, and I3 being on a time domain setup? Can you add them on that setup? No. So what are we going to do? What are we going to do in order for us to add all of those? Hmm? What are we going to do? Can we have Lawrence? Is Lawrence Belarma there? Lawrence. Are you there, Lawrence? Please, I join using your microphone so that I can hear you. So my question is, Lawrence, can we already add I1, I2, I3 in a time domain format?
Yes po, ma'am.
Yes? How?
Ano po ulit yung tanong, ma'am?
My question is, can we already add I1, I2, and I3 on that given format?
No po.
No. So what are we going to do in order for us to add this I1, I2, and I3?
I-convert po sa rectangular form po.
Rectangular form? How can we convert that into rectangular form?
Hmm, rectangular form. Hmm.
Okay, so what setup are we in? Take a look at the given, okay? Take a look at the given. The given are given in what domain?
Um,
Sorry.
in polar po, ma'am. Okay.
The given. Take a look at the given. These are the given, Lawrence. This one.
Yes.
Okay, the given, they are written in what? In what format?
Trigo po, ma'am.
Huh? What
Trigo.
what domain? Time domain, phasor domain, frequency domain.
Time domain po.
Oh, they are given in time domain. Now, my question a while ago is that can we already add this currents in time domain? You said no. Now, what are we going to do in order for us to add this time domains or to add this currents? What are we going to do? Hmm? What are we going to do? Is Lawrence still there?
Yes po, ma'am. Wait lang po.
Okay, Reggie. Oh, call a friend. Reggie. Is Reggie there? Can we have Reggie? Please join using your microphone. Okay? Join using your microphone so that we will not be having a hard time transferring from earphones to microphone. Reggie.
Yes po.
Okay. So my question is, can we already add these three currents on a time domain format?
No po.
No.
Guess lang.
Okay. So
Guess lang.
okay. So how can we add them?
I-convert po sa sa frequency domain.
Very good. So we are going to convert this one into frequency
Frequency.
domain. Okay. So what is the step in order for us to convert this three currents in frequency domain? Hmm? What is the first step? So let us convert I1 first. I1. The solution is already there. Okay? It is already written. So what is the first step in order for you to convert I1 into frequency domain? The original, ha? We use the original steps. Have you forgot our lesson last Monday? Reggie, are you still there, Reggie?
Yes po. 8. Ma'am. Kalimutan ko pa eh.
Okay, we have 20 sine omega t as your I1, right? And 20 is your what? What is 20? 20 is the IM, correct? 20 is your IM. Now, what are you going to do with your IM in order for you to get for the phasor equivalent? The phasor equivalent must be in IRMS angle theta, right? Correct? Am I correct? Hmm? So how can we convert 20 to IRMS? How can we convert IM to IRMS? We should divide it by square root of 2. Correct. So, we recall that IRMS is equal to IM over square root of 2 so that we can at least identify the phasor equivalent or the frequency equivalent of these three currents. Okay? So since we have 20 as our IM on I1, we can get for IRMS1. And our IRMS1 is equal to 20 over square root of 2. And that is 14.1. And the angle is, what is the angle in I1? 0. Very good. So we now have I1 as 14.1 angle 0 degree milliamps. Now we get the phasor equivalent of I2. How can we get for the phasor equivalent of I2, Russell? Russell. Is Russell there? Moral.
Hello po.
Okay, Russell. So how can we get for the phasor equivalent of I2?
Ano po? 10, I mean, sorry. I2, di ba?
Mm-hmm.
Yes, it's 10 then over square root of 2.
Mm-hmm.
And then after nun, makukuha 7.07 sa calcu.
Mm-hmm.
And then, yung, ano na lang, ma'am, yung degrees, which is 90 degrees.
Okay, where did you got 90 degrees?
From the given, ma'am. I know. Kasi
Okay.
10 sine over, I mean, 10 sine tapos plus 90 degrees.
Okay, very good. So that is I2. Our I2 now is 7.07 angle 90 degrees. So that is the phasor or frequency equivalent of I2. Now, how about I3? Can we have Eman Lastimado? Eman Oliver Lastimado. Eman there. Okay. Can we have Ronelo De Luna? Ronelo De Luna. Please join using your microphone. Then just mute your microphone so that we won't having a hard time from switching from the earphones to microphone. Okay, how about Andrea? Andrea, how can we get for the phasor equivalent of I3?
Hello, ma'am. Can you hear me?
Yes.
Um, First, we look at the equation, then get the IM, which is equivalent to 30.
Mm-hmm.
Then we will divide it by square root of 2 to get the IRMS.
Mm-hmm.
That is equivalent to actually, wait, let me calculate. 30 divided by, okay. So that would be equivalent to 21.2.
Mm-mm.
And the final answer would be 30 um, less than 30 less than negative 90. The negative 90 is nakuha doon po sa equation na omega t minus 90. So, yun po yung angle, yung phase po doon yung kinuha. So, yun.
Okay. It is 21.2, okay, not
Opo.
30. It's 21.2 angle negative 90 degrees. So
Ay,
this
sorry.
negative 90 degrees is from the equation itself, from the time domain, right? So since you have already got the 30 over square root of 20, that is 21.2, we already have the three currents from time domain format to the phasor domain format, correct? So, since I1 is 14.1 angle 0 degree, I2 is 7.07 angle 90 degrees, and we have I3 which is 21.2 angle negative 90 degrees, can we now add the three currents? Christopher Fernandez. Can we now add the three currents? Christopher Fernandez. Hmm. How about Cyron, Ezekiel? Cyron. Yes, okay. We can now add the three currents. So will you add them, Cyron, and give me the answer in polar form using your calculator? In polar form. So you just need to add 14.1 on your calculators. You can also do this one. You should add 14.1 angle 0 degree plus 7.07 angle 90 degrees plus 21.2 angle negative 90 degrees. What is the answer in polar form? Tyron. Please, others, you can also use your calculators to add the three currents. What will be the answer? Oh, what about now? Okay. So what will be the answer? In polar format. Polar form. It is 19.99 angle negative 44.98, or as you can see on your screen, because they use the manual setup other than using the calculator, it is 20.1 angle negative 45.4 degrees. Okay, so this is now our total current. Correct? This is now our total current. So since we already got the total current in phasor format, have we already got the correct answer, or have we already got the right answer onto the problem? Are we done? No. Okay. So according to Steve, we are not yet done. Okay, on answering this one. Now, Steven, what is the next step? What is the next step? According to the problem, we should determine, okay, we should determine the equation for the I total. So how can we determine for the equation upon getting the frequency equivalent or the frequency domain equivalent of the answer? What are we going to do? Okay, we should multiply. What are we going to multiply to square root of 2? What are we going to multiply? Okay, the amplitude. Now, why are we going to multiply the amplitude by square root of 2? Why? Okay, so that we can go back onto the time domain setup, because if the problem is pertaining onto the equation, therefore we must come up with the equation. And an equation format is on a time domain format. Very good, Steven. Okay, so since we already have 20.1 angle negative 45.4 degrees, and 20.1 there is our IRMS, we should convert our IRMS back to our IM. Now, how can we convert our IRMS back to our IM? We should multiply our IRMS to square root of 2. And by multiplying it, we could get 28.4. Okay, 28.4, and we should just write our equation as 28.4 sine omega t minus 45.4 degrees milliamps. Where did we get the 45.4 degrees? Where did we get the 45.4 degrees? Anyone? Where did we get it? Hmm? EE22S1, where did we get the 45, negative 45.4 degrees? Hmm? What if we don't know the arctangent 14.3 over 14.1? Where did we get the negative 45.4? Remember, you already have the IRMS, the phasor equivalent, which is equal to 20.1 angle negative 45.4. We got it from where? From this one, right? Onto the polar form. We just need to copy this one because this one is the phase angle and this one is also the phase angle required. So we just need to copy this one. Yeah? From the given phase. Correct? Are you following? Are you following? Okay. Now, what I'm pertaining to this one also is that what I have told you last time on our discussion last Monday is that there are some books, okay? There are some books who are not, or um which are not doing this kind of setup, or it means they are not implementing or they are not um applying the formula of IRMS, which will be like this. Okay, they are not applying it that you need to multiply or you need to divide your IM by square root of 2, then would get the phase or the frequency domain. Okay, we could actually just be on a direct format, and the direct format is this one. Okay, why do we uh can actually apply the direct format? Because as you can see on the first part of this step, we have divided square root of 2, right? We have divided the square root of 2. And at the end, we multiply square root of 2 again onto the final answer, which actually cancels out the whole process. Okay? It cancels out the whole process. It's just that you just lengthen the process of your solution. So that we can actually we can actually just do the direct format. And the direct format is that you can uh convert your time domain to your frequency domain directly. So if you have I1 which is equal to 20 sine omega t, you can just write I1 is equal to 20 angle 0. Then I2 is 10 sine omega t plus 90. You can just write I2 is equal to 10 angle 90 degrees. And you can have I3 is equal to 30 angle negative 90 degrees. Now, solve on your calculator this one. I1 plus I2 plus I3. So that is 20 angle 0 degree plus 10 angle 90 degrees plus 30 angle negative 90 degrees. And let's see if we would come up with the same answer. What is the answer if you would be adding 20 angle 0, 10 angle 90, and 30 angle negative 90? It is 28.28 angle negative 45 degrees. So since we have 28.28 angle negative 45 degrees, we can actually, okay, do this one into an equation format. Okay, we can already have it on an equation format. So that is 28.28 sine omega t minus 45 degrees, which is very close to the final answer. Did you get what I mean now? Did you get what I mean? That we can actually do the direct format if we are going back onto the original setup. But if we are not going back onto the original setup, let's stick onto the original steps. That you need to divide the square root of 2. If we are not going back onto the original setup. But if we are going back, or if the problem says that you need the equation format or you need the time domain format, you should, or you can do the shortcut. You can do the direct format. Are we clear about that? Are we clear about that? Okay. So moving on, we have the RLNC circuits, or the RLC circuits. So they have different voltage current relationship. So for the resistors, we have the Ohm's law. For the capacitor, we have the capacitor current relationship, wherein our current across a capacitor can be determined by multiplying the capacitance by the derivative of your voltage across the capacitor with respect to time. Then you can also get the inductor, or you can also actually evaluate the inductor and voltage relationship by getting the voltage across an inductor by multiplying inductance by the derivative of your current across an inductor with respect to time. Okay? So these are the three necessary formulas that you need to remember. Now, for the impedance concept, when we say impedance, okay, impedance is the opposition or the resistance that a circuit element presents to current in the phasor domain. It is defined as Z, which is the impedance, is equal to your Z angle theta. Now, when we say impedance, what do we mean by impedance? Impedance is the combination of R, L, and C. It's either, okay, our impedance can be either purely resistive. It means that your loads are all resistors. Okay? It can be purely inductive. It means that your load are all inductors. And it can be purely capacitive. That means that all your loads are capacitors. And it can be also, impedance can also be a combination of resistance and inductance. And impedance can also be a combination of resistance and capacitance. Impedance can be also a combination of inductance and capacitance. And in other way round, we can also say that impedance is a combination of resistance, inductance, and capacitance. Are we clear about this one? Are we clear about this one? So it can be a purely or it can be a combination. Okay? It depends on your loads. Okay? So next, we have the V is equal to IR. This is the very common the very common or the fundamental equation in electrical circuits, and this is the DC Ohm's law. The V is equal to IR, or our voltage is equal to the current multiplied by the resistance. Now we also have the Ohm's law, or the Ohm's law in AC circuits, and that is V is equal to IZ. So as you can see, our R on DC has been changed into Z because we are already dealing with inductance and capacitance as well as their combinations. So V now is, or our voltage now is equal to your current multiplied by your impedance. Okay? So for the impedance, it is a complex quantity that can be made up of resistance, which is the real part, and the reactance, which is the imaginary part. So if we will go back onto our idea on the complex number, which form of the complex number has the real part and the imaginary part? Which form of complex number? Rectangular form. Very good. So herein, Z is equal to R plus JX. Our R is our resistance or our real part. And our JX can be either, okay, this is now the reactance, which is the imaginary part. And our reactance can be either capacitive or inductive. Therefore, our capacitors and inductors can only be on the imaginary part. And our resistance can only be on the real part. Capacitive and inductive cannot be on the real part, because on the real part, that's only the resistance. Okay? As well as the resistance cannot be on the, or cannot be placed on the imaginary part. It is only on the real part. Are we clear about that? Are we clear? Okay. Now, the unit of impedance, of course, is ohms. And we have the what we call impedance triangle. Okay. This is the impedance triangle wherein the hypotenuse of the right triangle is the impedance itself. The adjacent side is the R and the opposite side is the X. Then we have a certain angle here. The cosine of a certain angle in AC circuits is the power factor. Okay, so in order for you to get for the power factor, so that is your resistance all over your impedance, your total impedance. Now we go on to the purely resistive circuits. So when we say purely resistive circuits, current and voltage are in phase. It means they are on the same speed, they are on the same setup. Okay, they are on the same displacement. It means their displacement is zero. Okay, so when we are dealing with resistors, okay, our when we say purely resistive, it means that the load, okay, the load across a certain circuit is only a resistor, or you have a lot of resistors connected with each other. Okay, but your loads are all resistors. That is purely resistive circuits. No other elements other than resistors. So that is purely resistive circuits. So when you have a purely resistive circuits, or your impedance is just composed of resistances, okay, we can say that our impedance or our ZR, since our loads are only R, or only resistors, so we label it as ZR. Our ZR is equal to R angle 0 degree. Okay? So what is the, let's say for example, if the value of your R is 15, okay, this will be 15 angle 0 degree. It is always 0 degree when it comes to resistances. Okay? So our ZR is now equal to R angle 0 degree. So we have an example here so that you can actually visualize. So we have two resistors, R1, which is equal to 10 kilo ohm, and R2, which is equal to 12.5 kilo ohm, are in series. So this is your R1 and this is your R2, and they are in series. Okay? We have a given I total, and our I total is 14.7 sine omega t plus 39 degrees milliamps. Okay, so we are asked to compute for VR1 and VR2, or the voltage across R1 and the voltage across R2. Then we are also asked to get for the voltage total in terms of VR1 and VR2. Then we are going to calculate for the Z total, or the impedance total. In DC circuits, this is the RT, or the total resistance. Okay? So since we are on AC, that is ZT. Okay? So we need, and letter D, we need to compare the total voltage to the result of the first one in terms of the total impedance naman. Okay? So, since we already have Z1 and Z2, or we already have your R1, sorry, R1 and R2, we can label this one that our R1 is our Z1 and our R2 is our Z2. So since we have also a given of I total herein, and we can actually say that we cannot manipulate the whole equation without what? Without converting our time domain format of the total current into what domain? Into what domain? Into phasor domain. So since we have a time domain format of 14.7 sine omega t plus 39 degrees, okay, we convert this one into a phasor domain format. So how do we convert this one into a phasor domain format? Christian J. Christian J. How do we convert time domain format to phasor domain format? Hmm? How about Jenkin? Lim. Jenkin Lim. How do we convert EE to S1? We are just repeating and repeating the process. I've already asked the same question for the nth time. Lance, Gio, Cruz. Can we have Lance? How about Maceda, Mark Joseph? Okay. So we convert time domain format to frequency domain because we cannot actually use this one, okay, to compute. So we need to convert it into a complex number format. And a complex number format is in frequency domain format. And in order for us to convert our time domain format to frequency domain format, we need to convert our IM to IRMS. And in order for us to do that, we need to divide it by square root of 2. So that is 14.7 divided by square root of 2. That would give us 10.39. And the phase angle or the phase offset is 39 as you can see on the given. Okay? So that would be 10.39 angle 39 degrees milliamps. So since we already have the I total, we can now compute for VR1 and VR2. How can we convert for the voltage in R1 and for the voltage in R2? We use the AC Ohm's law, correct? Because according to conditions, when we have a full series circuit, that our current is constant. Therefore, we can say that the current passing through R1 and the current passing through R2 is equal to your total current. Correct? So we can now use, in order for you to get for VR1, you can use the I1 multiplied by Z1. Okay? Wherein our Z1 is actually equal to your R1 angle theta. Okay? So Z1 now is this one. That Z1 is equal to R1 angle 0. And your R1 is 10 kilo ohm. So Z1 is 10 kilo ohm angle 0. And your Z2 is equal to R2 angle 0. And your R2 is 12.5 angle 0. Correct? So since in order for you to get for VR1 or V1, that is I1 multiplied by Z1. And your V2 is I2 multiplied by Z2. So your I1, which is equal to your I total, which is also equal to your I2, which is equal to 10.39 angle 39 degrees milliamps, will be multiplied by 10 kilo ohm angle 0 degree, and that would give you 104 angle 39 degrees volts. Same as true with the same holds true with VR2. So your VR2 now is equal to I2 multiplied by your Z2, wherein your I2 is equal to your I total, which is equal to your 10.39 angle 39 degrees milliamps, multiplied by your Z2, which is 12.5 kilo ohm angle 0. So that would give you 129.9 angle 39 degrees volts. Now we can already solve for our total voltage, because our total voltage can be solved by adding VR1 and VR2. So since VR1 is 104 angle 39 degrees volts, we can now add it to VR2, which is 129.9 angle 39 degrees volts. And that would give us 234 angle 39 degrees volts. Correct? So we have already solved A and B. Now we calculate for our ZT. According to series condition, we can get for the total impedance on a series condition by adding the individual impedances. And we have Z1 and Z2. Therefore, Z total is just equal to Z1 plus Z2. This one. Correct? Z total is just equal to Z1 plus Z2 since we are on a pure series circuit. So therefore, our Z total is equal to 10 kilo ohm angle 0 degree plus 12.5 kilo ohm angle 0 degree, and that would give us 22.5 kilo ohm angle 0 degree ohms. Now, letter D, we should compare our total voltage if it is the same on the total voltage we have got on letter B. And this is by getting our total voltage in terms of Ohm's law. And in terms of Ohm's law, that is equal to your total voltage will be equal to your total current multiplied by your total impedance. We already have the total current and we already have the total impedance. Therefore, we can now multiply them by each other. So that is 10.39 angle 39 degrees milliamps, which is your total current, multiplied by your 22.5 kilo ohm angle 0 degree, which is your total impedance, and that is equal to 234 angle 39 degrees volts. So if you are going to compare the two voltage total, they are just the same, or they are just of the same value. Okay, they are just calculated on a different formula, but of course, they will have the same value. They must have the same value. Is this example clear to each and everyone? Is this clear? Okay. So moving on, we have the inductance. So we will now deal with the purely inductive circuits. Okay. So voltage current relationship, as I have mentioned a while ago, we have the voltage current relationship for an inductor. So it is, in order for us to get for the voltage across an inductor, you should at least multiply the inductance by the derivative of the current across your inductor with respect to time. Okay? So therefore, we can actually say, since IL, okay, IL is in the time domain format, we can actually replace this one or substitute this one by the time domain format equation, and that is Im sine omega t. So this will be now our inductance multiplied by the derivative of Im sine omega t with respect to time. If we are going to get the derivative of Im sine omega t, we will be coming up with this equation that omega L multiplied by Im cosine omega t, since the derivative of sine is cosine. So we will now actually be converting cosine to sine. And in order for us to convert cosine to sine, that would be plus 90. If you would remember the cross. Okay? The cross, the conversion from cosine to sine and sine to cosine. So if we are going to convert cosine to sine, you have to plus, or you have to add 90 onto the equation. So this will be now omega LIM sine omega t plus 90 degrees. Now, how about the ZL? How can we get for the ZL? Or if the circuit is purely inductive, or when we say purely inductive, it has only the load is only inductors, or are only inductors. Okay, so when you have a certain circuit that its load is only inductors, or its load are only inductors, you could at least say that your ZL is equal to your omega L angle 90 degrees. Okay, always remember that your ZL is equal to omega L angle 90 degrees. Okay, and it should be noted that for a purely inductive circuit, voltage leads current by 90 degrees. That's why a while ago, if we are going back onto the resistors are in phase. Correct? They are of the same phasing. Okay? They are of the same. It means that their displacement is zero. That's why when we have a purely resistive circuits, our ZR is equal to R angle 0 degree. And when we have a purely inductive circuit, since voltage leads current by 90 degrees when we have a purely inductive circuit, we can say that our ZL now is equal to your omega L angle 90 degrees, wherein our omega is our angular frequency and our L is our inductance. Correct? Are you still following with what I'm saying? Are you still following with what I'm saying? Okay. So, since we have an inductive impedance, impedance can be written as a complex number in rectangular or polar form. Okay? So, since our circuit, if we imagine a certain circuit, okay? If we imagine a certain circuit and the loads of that certain circuit is only inductors, or are only inductors, we can say that our ZL, or the impedance on that certain circuit, is equal to your omega L angle 90 degrees in polar form. Now, in rectangular form, we have J omega L. As you can see, if we are going to tear, or if we are going to separate, okay, separate the Z, we have Z, okay, we have Z is equal to R plus JX, correct? A while ago. And this one is the real part, which is resistance. Then I have mentioned that this one is the imaginary part, which is the reactance. And the reactance is just composed of either inductive or capacitive. So since our load is purely inductive, and since our loads are only inductor, we can say that there is no real part. That's why it is just J omega L. Or we can say that this is just JXL, because XL, okay, XL is equal to your omega L, and XL is also equal to your 2 pi FL. Okay, because your omega is equal to 2 pi F. Are you following? Remember this one? Remember the equation that omega is equal to 2 pi F? Okay? Remember that? Hello? Okay. So since an ideal inductor has no real resistive, just like what I've told you a while ago, has no resistive component, this means that reactance X of an inductor is pure imaginary part. So we don't have a real part. On resistances, on purely resistive there is no imaginary part. We just have the real part. Now, on an inductive, we just have the imaginary part. We don't have the real part. Okay? So, always remember these equations because they are very necessary. Okay? So, again, voltage leads current by 90 when it comes to purely resistive circuits. And we always remember that for inductors, voltage leads current by 90. So, our ZL can be either be equal to omega L angle 90 degrees, or this in polar form. This is in polar form. And it is also equal to J omega L in rectangular form. So, we can also say that ZL is equal to JXL, or XL angle 90 degrees, wherein XL is equal to omega L, and your XL can also be equal to 2 pi FL, since your omega is equal to 2 pi F. Okay? So always remember these equations. Now, for the variation with frequency, since XL is equal to omega L and it is equal to 2 pi FL, wherein your inductive reactance, okay, this is your inductive reactance, correct, is directly proportional to your frequency. It means that in extreme cases, okay, wherein your frequency is equal to 0, or it means that your setup will be on a DC setup, your inductor will look like a short circuit. Okay? Your inductor will look like a short circuit. So if we have this circuit and you are already on a DC setup, okay, so from AC setup, you will be on a DC setup, your inductor will be shorted. Okay? It will be shorted. Okay? When we say shorted, it is just like a wire. It is just like a certain wire that is shorted. This is open actually. Should be shorted. Okay, so it should be shorted. Okay, so can we now have example number 7? So this is a purely inductive circuit. So for the inductive circuit, we have a given of VL equal to 40 sine omega t plus 30 degrees. We have a given frequency which is 26.53 kilohertz, and we have an inductance of 2 millihenry. Determine the VL and IL. Okay? So how can we determine for the VL and IL? So this is VL in capital letter. So it means it is in what form? VL will be in what form if it is capital letter? What format? What format? Hello? Do I have some students this morning? Can you see the PowerPoint? Why are you not saying you can see? Ay, how will you know the answer if you can see the PowerPoint? Why are you not saying something? If it goes black, tell it to me so that I know. How will I know if you won't tell me? Can you see it now? Okay, so I'll repeat the given. So for the inductive circuit, we have VL is equal to 40 sine omega t plus 30 degrees. You have a frequency of 26.53 kilohertz. And we have an inductance of 2 millihenry. So we are going to determine VL in capital letter and IL in capital letter. When we say VL and IL in capital letter, what do we mean by that? They must be on what format? What format? Hmm? They must be in what format? Hmm? What format? Time domain format, frequency domain format. Frequency domain format. Very good. Okay? If we are on a capital letter setup, it must be on a frequency domain format. Okay? So since we are given VL in time domain format, how can we get for the VL with the capital letter? How can we convert the time domain to phasor domain? The same question I am repeating over and over again. Okay, we divide the amplitude by square root of 2. Very good. So since we have an amplitude of 40, okay, 40, so divided by square root of 2, so that would be 28.3 angle 30 degrees. So that would be our angle, our phase offset, 30 degrees. So we already came up with our VL. Now, how do we get for IL? So since this is our circuit, okay, this is our circuit in here, we get our IL by what? By using the Ohm's law. Okay, by using Ohm's law, we can say that IL is equal to VL over ZL. We have the VL, but we don't have the ZL. How can we get for the ZL? The ZL now is equal to our JXL, correct? But we don't have an XL. Okay, so how can we get for XL? XL is equal to omega L, but we don't have the omega. Correct? So we can now say that XL can also be equal to 2 pi FL. We have F, which is 26.53 kilohertz, and we have L, which is 2 millihenry. So just substitute. We have 2 pi multiplied by 26 point. This is typographical error, so we will be using this one. So this will be now equal to your 2 pi FL or J2 pi F, which is equal to 26.53. Okay, 26.53 times 10 raised to 3 because this is kilohertz. Kilohertz. Okay, 26.53 times 10 raised to 3 multiplied by 2 millihenry, which is equal to 2 times 10 raised to negative 3 Henry. Since we have 10 raised to 3 here and we have 10 raised to negative 3 here, we can just cancel this out. Okay, so our ZL now is equal to 333.386 angle 90 degrees, or in rectangular form, that is equal to J 333.386. Did you get it? Are you still following? Okay. So since we already have our ZL, we can now solve for our IL. So since our IL is equal to VL over ZL, so that would give us VL, which is equal to 28.3 angle 30 degrees all over your 333 angle 90 degrees. So that would give you 85 angle negative 60 milliamps. Okay? So we already have the IL with the capital letter. Now, what if I want you to convert your IL, your frequency domain IL, into time domain IL? What are we going to do? What are we going to do? If I want you to convert your frequency domain to your time domain, back to your time domain, you multiply it by square root of 2. What are you going to multiply by square root of 2? The amplitude. Oh, we have the amplitude of 85. So that would be 85 multiplied by square root of 2. So that would give us 120. Okay, 120. Then sine omega t minus 60 degrees. Where did we get the minus 60 degrees here? Where did we get the minus 60 degrees? From the phase angle. Very good. Okay, did you get it now? Are you already absorbing the concept, the idea? Did you get it now? Okay. So we moved on our purely capacitive circuits. Can you see the PowerPoint? Can you still see it? Oh, what is going on? Can you see it now? Okay. So we now go on to the purely capacitive circuit. So just like your inductive circuit, actually it is of kind of the same, okay, kind of the same format, because when we say capacitance or purely capacitive circuits, it should be noted that for a purely capacitive circuit, current leads voltage by 90. So it is on the other way round. Okay, it's just on the other way round. It's just that instead of having ZL, we will have ZC. So ZC now is equal to your 1 over omega C angle negative 90 degrees. Okay, so instead of having positive 90, it would be negative 90 on capacitance. Okay, so 1 over omega C angle negative 90 degrees is the equation for ZC. So for the capacitive impedance, as I've said a while ago, since it is capacitive impedance and it is a purely capacitive or purely capacitance load, therefore we cannot have, okay, we cannot have our R or our real part. Okay, we cannot have our real part. So we can also say that our ZC is equal to 1 over omega C angle negative 90, or we can say this is in polar format and this one is in rectangular format, that we can say that it is equal to negative J over omega C in rectangular format. So since a capacitor has no real resistive, just like what in inductor, this means that the reactance of the capacitor is pure imaginary part. So this is just a pure imaginary part. We're in our ZC is also equal to negative JXC. Okay? Negative JXC, wherein our XC is equal to 1 over omega C. And we can also say that our ZC is equal to negative J over 2 pi FC. A over 2 pi FC. Now, how can we determine if a certain equation or a certain impedance is purely inductive or purely resistive? What do you think? What do you think? How can we determine if a certain circuit is purely inductive or purely capacitive? If you have a certain rectangular format equation. Let's say, for example, I gave you an impedance, okay? Or you have an impedance of equal to negative J 236 ohms. What is this one? Purely Inductive or purely capacitive? What is your load then? What composes a certain impedance if it is just J, negative J 236? Capacitive, inductive. How about now? Okay. So if you have Z is equal to negative J 236 ohms, what is that? Capacitive, inductive. Hmm? It is purely capacitive. Okay, it is capacitive because it has negative. Okay, it has negative. If you're always remember, guys, okay, that your Z, I have told you a while ago, right, that Z can be a combination of R, L, and C. Correct? And it can be also a pure of R, a pure of L, and a pure of C. Now, my question if Z is equal to negative J 236, it means this is a purely imaginary part. Correct? Purely imaginary part. So let's go back onto our discussion a while ago so that you can understand what I'm saying. Okay. So we have Z, right? Okay. And Z is composed of R plus JX. And our X can be of two. It can be capacitive. It can be inductive. And when we are uh, pertaining to inductive, this is positive 90 degrees. And when we are pertaining to capacitive, this is negative 90 degrees. So if I say that, and this is our resistance, correct? Now, if I say my Z is equal to 60, okay, 60 is just equal to 60. What compose my impedance? What compose my impedance? It is just, what do you think? It is just resistance, capacitance, a combination of RC, combination of RL, or something. If my Z is just 60, what is that? What compose my impedance? In Tagalog, ano ang bumubuo doon sa impedance ko? It is Andrea only my student? It is purely resistive. Very good. What if my Z is equal to J60? What is my J is equal to J60? It is purely inductive. Okay? Purely inductive. Very good. What if my Z is equal to negative J60? Oh, this is purely resistive. Okay? This is purely inductive. And this is purely what? Capacitive. Okay? This is purely capacitive. What if my Z is equal to R plus or sorry. What if my Z is equal to 60 plus JXL? What is or sorry, equal to J50? What is the nature of my circuit then? Is it Not purely, but is it capacitive or inductive? Basically, this is not purely. Okay? It is a combination. Or what is the combination of this one? My Z is a combination of what? What are the loads that compose my impedance then? Inductance and resistance. Very good. So we have R here and we have basically X here. Now, what is the nature of your X? Is it capacitive or inductive? Inductive because of the positive sign. So therefore, this is XL. Correct? Now, what if I have Z is equal to 60 minus J 50? What compose my Z now? Resistance and capacitance. Very good. So we have resistance and we have capacitance, or we have our reactance, which is in what nature? What is the nature of our uh reactance here? Capacitive. Okay? So it is capacitive. Did you get it now? Did you get the impedance concept now? Okay. I hope it is clear now. Okay, so capacitance, always remember that current leads voltage by 90. That's why it is denoted by negative 90. So always remember, for capacitors, current leads voltage by 90, and our ZC is equal to negative J over omega C. Okay, negative J over omega C, or 1 over omega C angle negative 90 degrees. We can also say that ZC is equal to negative JXC. Okay, wherein our XC, yes, Francis. Okay. So wherein our XC is also equal to 1 over omega C, or equal to 1 over 2 pi FC. That's why ZC can also be written as negative J over 2 pi FC, or our ZC can also be written as negative J over omega C. Okay, so always remember these equations. Now, for the variation with frequency, or for the frequency dependency, since XC is equal to 1 over omega C, we can say that our capacitive reactance is inversely proportional to frequency. Therefore, in extreme cases, or when we are dealing in DC instead of AC, our capacitor looks like an open circuit. Okay, when we say open circuit, your circuit will be disconnected from the whole setup. Okay, it has been disconnected onto the capacitor side. Okay, onto the capacitor side. So always remember Ellie the Iceman, so that you will not forget about it, that when you are dealing with inductance, voltage comes first before current. It means that when you are dealing with inductance, voltage leads current. And when you are dealing with capacitance, current comes first before the voltage. It means that your current leads the voltage when you are dealing with capacitance. Okay? And of course, for the frequency dependency, I would just want to repeat it. For the inductors, during DC connection or during DC setup, your inductors acts like a short circuit. But during high frequencies, or on frequencies that is not regulated, it means your inductor will be open. And for the capacitors, when you are dealing with the DC setup, or when you are dealing under DC setup using capacitor, it will be an open circuit. And during high frequencies, your capacitance or your capacitors will be